So we're now going to look at some examples of singularities and their type. So 1 over 1 plus z, obviously this is going to go to infinity as z goes to minus 1. So that tells you that you've got a pole of some kind. And it's a simple pole. Really, I mean, the simplest way to think of it is that if you were to plot the real function 1 over 1 plus x, I'd say the simplest way to think about it is that, well, look at 1 over it, and that's going to have a simple 0. So 1 plus x or 1 plus z has a simple 0 at z equals minus 1. Simply because if you plot y equals 1 plus x, then that crosses the x-axis at x equals minus 1, and it crosses with a gradient which is not 0. I mean, it crosses properly. That's all the mental processes you need to work out that it has a simple pole. You don't really need to do anything else. So, I mean, most things tend to be simple poles. If they look simple, then the chances are it's going to be a simple pole. Okay, next one. E to the z over z to the 4 has a pole of order 4 at z equals 0. Well, why is that? Well, in this case, again, you can think of it as, well, there's different ways of doing it. You could do the Laurent series and say, well, okay, the Laurent series is the series for e to the z, and then you divide that series by z to the power 4. So you know the series for e to the z is 1 plus z squared over 2 factorial plus etc. You divide that by z to the 4, and obviously you start off with 1 over z to the 4. Compare that with the Laurent series, you've got b4 is 1, z0 equals 0, obviously. So therefore it's a pole of order 4. But actually, another way of doing it is, again, you think of it 1 over this. So at z equals 0, e to the z is well behaved, it's analytic, and it's not 0. E to the 0 is 1. So you just think of 1 over this, and you've got a 0 of order 4. So if you do 1 over a 0 of order 4, then you've got a pole of order 4. This is a more interesting example. E to the 1 over z. Again, this is not something you're going to see in a physics equation. But e to the 1 over z, if you think about what the series for that is going to be 1 plus 1 over z plus 1 over z squared over 2 factorial plus 1 over z cubed over 3 factorial. So basically, you're going to have an endless supply of non-zero b's. So that means it's going to be an essential singularity at z equals 0. Okay, this function here. Okay, well, when z equals 0, basically you've got 1 over z times itself 3 times. So 1 over z is a pole of order, a simple pole. Simple pole times itself 3 times gives you a pole of order 3. That's one way of thinking about it. And here you've got 1 plus z squared, right? So this is where you have to think, well, I can factor this 1 plus z squared, and I can factor it as 1 plus iz times 1 minus iz. Well, that's one way of thinking about it. So, which when you multiply together gives you 1 minus iz squared, which if you multiply out the brackets gives you 1 plus z squared. Okay, so that gives you the solutions z equals plus or minus I, or you can just have a look at that. The fact that you've got a factor of 1 plus iz tells you immediately it's sort of like this case here. Each of these is going to be a simple pole. Okay, this one is more interesting example, quite an important example. Obviously, when z equals pi, sine z is 0. You're dividing by z minus pi cubed. So basically, you've got a product of a simple 0 at z equals pi and a pole of order 3. This, if you had 1 here instead of sine z, you'd have 1 over z minus pi cubed. That would give you a pole of order 3 at z equals pi. But if you multiply a pole of order 3 by a 0 of order 1, then you get a pole of order 2. So that's the way you think about these things. You look at what's on the top. Is it 0 or not? If it's 0, then you think, okay, what order of 0 it is it? And on the bottom, you look at, also, you can just look at the bottom and say, okay, that's a 0 of order 3. And a 0 of order 1 divided by a 0 of order 3 gives you a 0 of order minus 2, which is the same as a pole of order 2. So there's different ways of looking at this. None of them actually involve getting the Laurent series, which takes too much effort. Okay, so Sheck Z, if you remember, Sheck Z is 1 over cosh Z. So we know that cosh Z has simple zeros, at these values of Z, which means that 1 over cosh Z, which is Sheck Z, should have simple poles, not simple zeros, simple poles at these values. Okay, so this function here, e to the z, 1 over 1 plus e to the z, again, why are they simple poles? Well, because 1 plus e to the z has simple zeros at these values of z. Again, can we explain why they're simple zeros? Well, with some effort, you can actually differentiate. Yeah, I mean, okay, you can differentiate 1 plus e to the z and check that it's not 0 at these values. But you have to have good reason to actually for it not to be a simple pole. We will need to know what type of pole these various singularities are later, very soon. With experience, you just look at it and you say, okay, this has got to be a simple pole. There's no reason to suppose it's going to be anything else. When you're starting out, you might like to verify it really is a simple pole. But again, I stress the simplest way to do this is actually to look at 1 over the function and say, okay, is it a simple 0? If you're not convinced it's a simple 0, in this case, it's a little bit tricky because the number's complex, or imaginary. So it's not you can't just plot 1 plus e to the x and look where it crosses the x-axis, because it doesn't. But basically, then maybe then you have to actually differentiate and look at what e to the z is at these points and see that it's not 0. Well, it's fairly obvious it's not 0 because it has to be minus 1, which is not 0. And finally, e to the z actually has no singular points except at z equals infinity. But okay, these are for z in the complex plane, which doesn't include infinity. Okay, so I think for this graduate course, I won't go into all of this. So this is for your interest if you want to read about what you do, if you want to include points in the extended complex plane, which includes the point at infinity. So when you answer question 15, you can change this extended complex plane to just the complex plane, if you wish. Now, I think if you have Mathematica, then well, whether or not you have it or not. I'm going to mention um, functions in Mathematica that you might find useful. Um, I believe there's a website, something called, like, it might be wolfram.com or something like that, where you can actually type in Mathematica functions. You can type in commands to Mathematica and it will give you the answer. So if you don't actually own a copy of Mathematica, then you can use that. Mathematica's, I do recommend using it. I mean, it's good for checking homework. It doesn't really do the homework for you. It won't tell you the working, so you still need to do the homework, but it's good for checking answers. And as a research tool, it's obviously invaluable for checking things. It's a program that's been going on for a long time. I'm not quite sure when it started. In the 1980s anyway. So, I mean, it started off with quite a lot of bugs, but it's now a lot better than it was. So generally it tends to give the right answer. Anyway, I'm going to now and again mention functions in Mathematica which you should find useful. But the series function will automatically give you a Laurent series expansion if your function has a singularity at z0. Otherwise, it just defaults to the Taylor expansion. So I've just given an example. So in this example, we're talking about here. Is that the one I meant? No, sorry, it's this one here. So you can check that you got simple poles just by looking at what series you get when you do this. Type all of this in, and you should find that the series just has one B term. It should have a B1 and all the other B2 and so on over 0. Okay.